American Society of Naturalists Symposium. I want to first thank all of you for attending this morning and thank the speakers for being willing to share their work, and also to say thank you to the American Society of Naturalists for selecting this symposium on the causes and consequences of fluctuating selection. So today we're going to be hearing work that examines several different aspects of fluctuating selection. We're going to be hearing some work that examines some advances in theoretical models examining the dynamics and stability of fluctuating selection in the wild. We'll be hearing work that examines the environmental drivers of fluctuating selection in the wild, and then trying to think about how this work situates in an ecological context by thinking about how rapid adaptation across time in response to fluctuating selection pressures has ecological consequences in terms of the population dynamics of a focal species, but also in terms of the interactions between species within an ecosystem. So what I want to do over the next few minutes as we get going this morning is to provide a little bit of a background to some of these topics and to kind of introduce what we have sort of historically known about fluctuating selection and how it plays out in the wild, and to try to set the stage for what we'll hear about for the remainder of our symposium today. So how organisms cope and populations adapt to fluctuating selection pressures, or how they respond to fluctuating selection, is central to our understanding of phenotypic diversity across all of life. And it's long been appreciated that fluctuating selection can promote phenotypic diversity, and much of this work was sort of spurred by early ecological geneticists who were interested in studying and examining basically how the environment acted to modify populations and shape phenotypes. So we can think about the relationship between fluctuating selection pressures and phenotypic diversity in sort of two very broad ways. On the one hand, we can view fluctuating selection as a generator of phenotypic diversity through its role in phenotypic plasticity. And in this sort of circumstance, we can imagine that we have an environmental factor which modulates a phenotype, but it doesn't change the genetic composition of that population. So when this happens, the question is, when do we expect phenotypic plasticity to arise, right? And typically we think about phenotypic plasticity arising when individuals are dispersed across a highly varied landscape, when a particular individual or genotype experiences a wide variety of different types of environments. So we can think about this in the context of dispersal. We can also think about it in the context of the lifespan of a single individual, in which they might, over the course of their life, experience a diversity of environments. And over the course of experiencing those diversity of environments, they change their phenotype and behavior, right? So this is plasticity. The other way, the other sort of fundamental way we might think about how environmental variation and fluctuating selection pressures promotes phenotypic diversity is thinking about adaptive tracking and local adaptation. So in adaptive tracking or local adaptation, we again have some change in phenotype across an environmental gradient, but that change in phenotype across an environmental gradient might be due to changes in allele frequency as they change in response to selection pressures that vary through time and space. And adaptive tracking and local adaptation are potentially thought to arise when dispersal might be more limited, right, where populations experience only a subset of possible environments, or when across time, right, when individuals experience or generations experience only a subset of environments that a whole population might experience over multiple generations. So during our talk today, we are going to be focusing on the temporal dynamics specifically, or primarily focusing on temporal dynamics and how they relate to patterns of phenotypic diversity, with a particular focus on how temporal fluctuations in selection pressure through time affect the adaptive dynamics of populations, with these consequences on ecosystem processes. All right, so just to kind of recap a little bit, we're going to be focusing on these theoretical models which examine the stability and molecular signatures of adaptation in response to fluctuating selection. We'll be examining work that explores the environmental drivers and trying to understand the environmental drivers of local adaptation and backward tracking, and then thinking about the ecological consequences, both in terms of the impact on and stability of interspecific interactions. All right, so I'm going to kind of outline a little bit of the history of some of these fields and talk about some of the recent advances in these different fields. So much of the work sort of thinking about the dynamics of temporally varying selection from a theoretical perspective and historically, right, stemmed from early observations about the nature and extent of genetic variation within populations. And many of the early models, seeking to examine and understand the role of fluctuating selection, sought to examine how fluctuating selection might promote the observed genetic variation that was being seen in many natural populations during the mid-20th century, beginning of the mid-20th century. So many of the models that sought to examine the role of fluctuating selection and the maintenance of diversity, right, were published in AMNet, and so AMNet has a long history in thinking about this particular topic. And this is by no means an exhaustive list, but I wanted to just highlight a few of the sort of earlier papers that sought to examine this work. So work examining just the basic nature of adaptive polymorphism within populations. Work that examined the sufficient conditions for polymorphisms to be maintained through multiple niches, right, through this sort of variation in the environment. And then trying to examine how combinations of both temporal and spatial factors sought to maintain diversity within populations. So there's two sort of very classic papers which set the stage for thinking about natural variation in populations, and that was work by Howard Levine and Halbane and Jayakar. And this work sought to examine what can be generally understood to be viewed as marginal overdominance, which is when basically the heterozygote average across different types of environments has a higher fitness, and that is a sufficient condition in many cases to maintain genetic variation in response to fluctuating selection pressures. So you can imagine a simple situation where you have 3 different genotypes at a locus that have different fitnesses in different environments. In an additive case, you might have a situation like this, where you have these sort of crossing reaction arms of fitness. When you average across environments, you may end up where you have a heterozygote having a higher fitness than either homozygote. And that can be a condition for the long-term persistence of polymorphism in populations in response to these fluctuating selection pressures. So in response to sort of spatially varying selection pressures, we can envision that the harmonic mean of this heterozygote has to be higher than the homozygotes for this sort of protected polymorphism. And for temporally varying selection, the sort of classic model suggested that the geometric mean was necessary in order to promote polymorphism for long periods of time in response to fluctuating selection pressures. Now, I think many of us have heard, and we oftentimes teach in class or talk to our students, that temporally varying selection might be inefficient in maintaining genetic variation relative to spatially varying selection pressures. And this is not a new view. This is a view that's been kicked around for a long time, and there's some good reason for that. One reason is purely mathematical, right? Because of the relationship between the harmonic mean and the geometric mean, we might expect that temporally varying selection might be more inefficient in maintaining genetic variation than spatially varying selection pressures. And these sort of models, which make these sorts of claims about the relative efficacy of temporally versus spatially varying selection pressures, have been expanded, right? And so you think about different conditions of these models. And we might even go so far as to conclude that in response to temporally varying selection pressures, you might actually lose genetic variation faster than you would in response to for a neutral locus. So if you think about factors like the autocorrelation of environments across generations, you can envision how genetic variation is lost more rapidly than even at a neutral locus. This led some to conclude that temporally varying selection pressure, while it might be important, it might be relatively not that important for maintaining genetic variation in response to polymorphism in the environment. Okay. So one of the issues with this is this problem of specification, right? That there are too many models in order to understand sort of the breadth of these complexities of temporally varying selection pressures. And so it really has spurred this long development of different types of models in the field, which we're going to hear about today. All right. I think that we're at time, and so I'm going to stop and bring up the next speaker. Is Moises.